So we're going to walk through this example of a proof by contrapositive. So we're asked to prove that for all integers n, if n squared is even, then n is even. So if we're thinking about this as an implication, then our hypothesis, or the p part, would be that n squared is even, and the conclusion, or the q part, would be that n is even. Okay. So I say this in the notes, but in general, when you're trying to prove something in mathematics, we're often not told what proof method we should be using, but here I am going to tell you that we should use a proof by contrapositive. So the reason for that is if we were to try to prove this directly, we would get to assume that n squared is even, and then we would be wanting to show that n squared is even, and that's going to be rather difficult because there's not really a direct way to, let's say, take the square root and show that n is even. So instead we want to do a contrapositive proof. So remember, the contrapositive of the implication, P implies Q, is the negation of Q implies the negation of P. Okay, so basically what we want to do is we want to prove this instead of the original implication. So the idea here is that the contrapositive is logically equivalent to the original implication that we started with. So if we prove the contrapositive, that means the original is true also. Now, when we want to prove this, we get to assume the hypothesis part, which in this case is the negation of Q, and then we want to show that this is true. Okay, so in other words, we get to assume the negation of Q. Well, remember, Q is up here, is the fact that n is even. Okay, so in other words, we get to assume that it's not true that n is even, which in this case, since we're talking about integers, that means that n is odd. Okay, well, and remember that what we want to show, is that n squared, so we want to show the negation of P being right here, so the negation of that would be that n squared is not even, or that n squared is odd. All right, so I'm just going to do the scratch work here. The formal write-up of this proof is in the notes, but hopefully it's going to give you an idea. All right, so basically what we want to do is recall that up here we're trying to prove this for all integers n. So we would say let n be an arbitrary integer and assume that n is odd. Okay, so what does it mean that we have an odd number? Well, then we know there exists an integer k, so I'm going to kind of write this in shorthand here because, again, the formal write-up is in the notes. So that means there exists an integer k such that, remember, an odd number is equal to 2 times an integer plus 1. Okay, so that's basically what we can say just off of our assumption. Now, remember that what we want to show up here is that n squared is odd. So it might make sense to take this n and just square it to see what happens. All right, so then let's just do that. So n squared would be 2k plus 1, whole thing squared. All right, and I'm going to write this out, kind of the whole thing, just to make sure we all remember that when it's squared, we need to actually FOIL it. So 2k times 2k would be 4k squared. The outside is 2k, inside is 2k, and the last is 1. So if we kind of combine like terms there, we get 4k squared plus 4k plus 1. Now, what we want to show again, we're trying to show that this n squared is odd. Well, n squared is equal to this. How do we show that something is odd? Well, we show that it's 2 times some integer plus 1. So we're going to take just these first 2 terms here and factor out the 2. Okay, yes, the greatest common factor is actually more than just 2, but because we're trying to show that it's odd, we want to just factor out the 2. All right, so if we factor out the 2 just out of the first 2 terms, then we're left with 2 times 2k squared plus 2k plus 1. So now what we would say here is that, of course, 2k squared plus 2k, whatever that is, it's an integer, right? Because k is an integer. Thus, we have 2 times an integer plus 1, which is exactly the form of an odd number. So we can conclude that, therefore, n squared is odd. Okay, so what did we just do? We started with an arbitrary odd number. We showed that n squared is odd. Why did we start with an odd number? Because we were assuming the negation of q is true, and we wanted to show the negation of p. So what we've done, kind of without formally writing it up, is we've proven the contrapositive of the statement that we wanted to show. But again, since that's logically equivalent to the original implication, we can conclude that the original implication is true also. So I'm going to refer you to the notes for kind of the formal write-up of this. This is kind of the quote-unquote scratch work, because remember, when you're writing a proof, you should write in full sentences. So that's shown in the notes.